All right, so we'll continue on the economic dispatch for generation. So the background of the background methodology to solve this problem is optimization. On Monday, we started from unconstrained optimization, which means you have a cost function you want to minimize. So how to find the local minimum points, and then we can find the global minimum. So there are a necessary condition and a sufficient condition. The necessary condition means you need to find where the gradient vector becomes 0. So that indicates the value of the cost doesn't change at that point. So that point can be a minimum point or a maximum point. So next step, you can check the sufficient condition for local minimum. To do that, you have to calculate the Hessian matrix, which has all the second order partial derivative of your cost function with respect to the change of the each state value. If the Hessian matrix is positive definite, which means it will, in all directions, the cost will increase. And also slope will of the function value with respect to the state will also increase. So that will be the minimal point. So by checking both conditions, you actually can identify 2 stationary points. For this simple example, by checking the second condition confirmed, this point will be the minimum. So this is very simple case. If you don't have many variables to solve, so you're dealing with a lower dimensional problem, you can skip. You may skip the second condition, the service condition. You only check necessary condition. By checking necessary condition, you identify all the stationary points, and then you calculate the function values at all the points. And the one taking the minimal value will be the final solution. This is unconstrained optimization. So when we come to a constraint optimization, we add one equality constraints. So which means you're not free to change all the variables. So all the variables need to meet this equation. So that narrow down the space or the room for the variable to vary. So they have to, no matter like how they change, they have to always need to make this equation hold. And if you solve this equation without calculating any function values, the solution to this equation are called feasible solutions. The feasible solution means if all the state variables are taking values, take value that meet this equation, those state variable will present a reliable condition. So for power system, such equation can be power flow equations, for example. If all the voltages, currents, or angles, powers, they can satisfy this equation, the system is normal. It's operating under a normal condition. If there are multiple normal conditions, then we want to find out how to minimize this cost function. We find the state with the minimal cost among all the feasible solutions. So that's our goal for economic dispatch. So the logic is to find the feasible solution is not too bad. It's okay. That can at least guarantee the reliability of your system. If you have more room to choose between different solutions, and we want to find the cheapest one with the minimal cost. To solve this problem, you can definitely first solve it as unconstrained optimization to find the gradient vectors, and then form the Hessian matrix to check the sufficient condition, necessary condition, and then you try figure out how to apply these equality constraints. But there's a simple way. You actually can form a new problem, which is unconstrained optimization problem. So you still try all the technique with unconstrained optimization problem. So such method is called Lagrange method. So by introducing a Lagrangian function, Lagrangian function is just an extended cost function. Instead of minimizing f, we want to minimize or find stationary points of this new function. The new function has all the variables from original problem and also introduce some new variables. So the physical meaning of each new variable is the price you're going to pay for violating any constraint. So if you have a k constraints, equality constraints, you introduce k multipliers. We call it Lagrange multipliers. So each multiplier means certain price you want to apply to the violation of each equality constraints. So here means if any g is 0, okay, so which means you don't need to pay any price. Being 0 means that equality constraint is satisfied. Then you don't need to pay any price. If g is not 0, like for example, it's bigger than 0, so you need to pay some price. So that value of g multiplied by the price will add the cost to this Lagrangian function. Okay, so that's the logic. But by doing this introduction of a Lagrangian function, so we can solve this new problem as unconstrained optimization problem. As I said, because here we don't deal with a very high dimensional problem, so we can only check a necessary condition. We only just find the stationary points of this new Lagrangian function. And then we check function value of each point to find the minimal one. We just skip over the step of forming the Hessian matrix and check whether it's positive definite or negative definite. We don't do that. We just check stationary points and find the minimal function value. Okay, so then we still take this the first step for the necessary condition. We find the stationary points. So by finding stationary points, you have to calculate partial derivative of this new Lagrangian cost function with respect to each variables, including original variables and also the new variable, this lambda, the price or the multiplier. So you can tell, so for when we calculate such a partial derivative, so that is equivalent to make that equality constraint hold, because this is exactly our equality constraint. So we don't lose anything. We keep every information from original problem, but we just treat x and lambda here equally about the variables to be determined to find the solution. So then you just go ahead to find to solve those equations, and the solution will give you all the stationary points. Okay, let's visualize this process by a simple example. We still consider this example in our unconstrained optimization problem. So we know this cost actually find any point in the two-dimensional space or the two-dimensional plane, any points the distance to the origin. We want to find the smallest distance to the origin, right? So it's a trivial problem. If we don't add any constraints, the solution has to be the origin itself. Then you have 0 distance. Because you move away from any point to any point from the origin, that distance will be non-zero. Okay, so that's a trivial. But now we add equality constraints. So we want any points staying on this equation. We find the minimal distance to the origin. So what is this equation? What does this equation tell in geometry? Right. So you can quickly recognize it is a circle. So it is a circle centered at 8 and 6 at a radius of 5, right? Okay. So we want to stay on that circle. And we found the point closest to the the origin. So that will be the final solution for this problem. So you can definitely solve this problem using your knowledge of geometry. You draw the circle, and by finding the distance, you actually can easily find where the distance is the smallest. But here we want to demonstrate how to solve this problem completely using our Lagrange multiplier method. We don't have to know the geometry, because when you deal with a slightly more complex problem, you don't, if the dimensions go beyond 3 or 4, so it's not very likely to draw the geometry, right? To use geometric method to solve it. First, we want to convert the equation into the standard form. In the standard form, we have left-hand side, we have some nonlinear function, g. Right-hand side, we have 0, right? So this g is equal to 0. So this will be our standard. So this part will be the nonlinear function, the nonlinear function for the equality constraints. So next, we just introduce this Lagrange function. So if the first part will be exactly everything from the nonlinear cos function, and the second part will be from the gxy and multiplied by multiplier lambda, because in this case we only have just a single equality constraint, so we only need one lambda. If you have two constraints, you need two lambda. So this is L. Okay. So next step is to calculate the gradient vector for L, considering the change in all directions. So right now we have three directions to change. We can change in x direction, y direction, the lambda direction. So you have to calculate the 3 elements of the gradient vector. So partial L by partial x will be this one, and partial L, partial y, and the partial L, partial lambda, it will be simply this one, right? So to find that element, we treat only lambda as a variable. So x and y will become a constant. So partial L, partial lambda is simply just equality constraint itself. So this is why we didn't lose any information from the original problem. So now from here, we just go ahead to solve those 3 equations with 3 variables. And if you solve it, for this specific set of equations, it's not hard to solve. But if it's more complex, we already know how to solve nonlinear equations, right? So how do we solve nonlinear equations? From a previous section. In general, we have a Gauss method, we have a Newton method, right? You can choose either way. Okay, for this one, you can simply just try Gauss method to give some initial guess. Newton methods allow you to introduce the Jacobian. You can know the slope that will take a fewer iteration. Okay, so I just go ahead to give you the solution. So finally, there's only the two solutions, which can have the 0 gradient vector for the Lagrange function. So there's two solutions, and you plug in the 2 solutions back to you plug in the x and y, because here we want to minimize f, right? We want to minimize f, and you plug in x and y back to the f. So the first solution has f value 225. The second have 25. So you know the second one will be our final solution. Okay, so the problem is done. It's solved. We don't utilize any knowledge about the geometry. We can solve this problem. So you can apply this approach to any more complex cost functions and any number of equality constraints. You just go ahead and try this step. If the dimension is not extremely high, so the candidate solutions may not be many. So you just check their cost function one by one to see which one is the smallest. definitely it may take some effort to solve those nonlinear equations. You may want to utilize the Gauss method, Newton-Raphson method. Yeah, so that's it. That's a technique we're going to use in our economic dispatch. Let's visualize what happened during this process. Okay, so in this two-dimensional plan about S and Y, each green circle indicate where the gradient vector will have the same magnitude, but the direction will be leaving from the origin. It will be opposite, which means if you draw a straight line starting from origin, that will be on that straight line, right? That's leaving. So any point on that circle will have a gradient vector leaving from circle. And if you move further from the origin, which means that you have a bigger circle and the vector will be longer, which means that's the direction of cost function to increase. So when we don't have the equality constraints, so the only solution will be origin itself, because at origin it's only the stationary points for this case. Because it is a quadratic cost function, it only have just single. For this case, only just have a single stationary point. But now we add this equality constraints, and we know that it's a circle. So if we draw the circle, that's origin circle there, centered at x equals 8, y equals 6, and the radius of 5. Okay. By adding this circle, we introduce multiplier lambda, single lambda. So we add another dimension. But this plot is only 2 dimensions. So we didn't draw the third dimension. Okay. So in the third dimension, there's also a gradient vector with respect to lambda, which is such element. So this element also introduce some directions that make L not be the stationary points. Okay. So which means if we investigate all the 3 dimensions, eventually the candidate solution have to be stationary points of L, even it's not F, because only a stationary points of F will be the origin. But now we study L, so we find stationary points of L. So let's visualize what happened. So this is feasible solutions. We need to stay around this circle to find where the cost of function F will be minimized. So the final, let's see why those 2 candidate solutions are candidate solutions. The candidate solution, they have to be stationary points of L. So let's see the orange point. The orange point, I draw a little green arrow that indicate the gradient vector of F. So that is not 0. So which means that point definitely doesn't look like a solution, because that's the direction the cost will increase. If the cost will increase, which means we need to move it in the opposite way, right, to reduce the cost. But because there's a constraints that limit where this orange point can move around, so it cannot move. It have to stay on the circle. So which means the Lagrange multiplier introduce additional force to try to put this to make this ball stay there. Okay, so we can draw also the gradient vector due to the equality constraints. So at this point, which is like there's 2 directions for the price can increase if we investigate this point. So if this point move a little bit inside of the circle, so there will be a price. We'll have to drag it back, because you're going to pay some price. It's violating this criteria. If you move a little bit outside, there seems to be another penalty added here. So finally, for this case, we have 3 arrows added to that point. We have 1 green one, 2 orange ones, and they're completely in parallel. Okay, so that explains why this point can be a solution, because there all the forces of 2 different directions vanished. They canceled out each other. So make with that point to be a stationary point in the higher dimension. Similarly, this right one also have the one green arrow pointing the inside of a circle, and also two orange arrows. One is pointing to the inside, one is outside. So they're also completely in parallel. They cancel out at that point. Then next question will be, why is this point not a candidate solution? It is a feasible solution, but you see the two orange arrows, they can they're in the same line, but there's also green one. Okay, so green one is not in parallel, which means for this smaller green one, it can have a two component. If we investigate this little green arrow, it has a little component in parallel with the orange line arrows, and another small component try to move this ball along this circle, which means it cannot stay there. So all the visualization you're looking at right now is the projection from a higher dimension. So which means finally, only those 2 points can be stationary points of L. That explains why we can calculate the gradient vector of the new Lagrange cost function and find stationary points. All the stationary points, they are like a state in this space. They have all the forces added to the point will cancel out. So at each candidate solution, all gradient vectors cancel out like balanced forces. This is just a geometric explanation about this Lagrange multiplier method. We don't want to utilize this geometric method for higher dimensional problem. We just try to give you better idea, try to explain how we can transform this constraint problem to an unconstrained problem, and why the gradient vector being 0 is that important. Any question? Okay, clear? All right, so next step, we'll add a new type of a constraint, which inequality constraints. So by inequality constraints, which could be like a generator, they have to operate within their operation limit, like a generator of capacity of 200 megawatt, and its power has to be lower or equal to the 200 megawatt limit. So then we can use this inequality constraints to model such a constraint, such a condition requirement. So any inequality constraints actually will be written in this way with U be either less than 0 or equal to 0. So which is equivalent to 2 constraints. So if either one is satisfied, that will be considered as a feasible solution. So U can be 0 or can be negative. If it's a 0, it will be similar to equality constraint. If it's a negative, that will be a requirement. Right? You have to you have to make sure that can be satisfied. So the idea to solve the optimization with equality and inequality constraints can be like this one. So we borrow the idea from the optimization with equality constraints. We first solve the optimization with equality constraints only. Okay. Also, if this equality hold, so we can add that one also to the equality constraints. So we just find the stationary point for the new Lagrange functions. And another, we need to address this one. We also need to make sure if this equality constraint is not hold and this is true, that's also good. Okay, yeah, let's go to the detailed step how to solve this problem. All right, so first we introduce Lagrange multiplier, lambda and mu. Lambdas are only for the equality constraints for G functions, and the mu's for the inequality constraint for the U functions. And here we want because the lambda mu will mean some penalty. So usually we assume the penalty to be positive, or at least not negative. When we deal with the equality constraints, we only introduce lambda. We didn't mention the lambda has to be positive and negative, because for that case, we want the stationary points. We want to find stationary points of Lagrange function. Once you find the stationary points, and that will make sure the equality constraints can be satisfied. But here, because we have inequality constraints, so we only want the state to stay on one side of this U, right? U can be 0 or negative. Then we have to define the sign for mu. The mu has to be, it cannot be negative. So make sure this one give you a meaningful penalty or price. Okay, so the L is just simply the linear combination of original cost function, the total penalty of violation of equality constraints, and the total penalty of a violation of inequality constraint. Okay, so we have one cost, two penalties. So next step, we only check a necessary condition. Don't worry about the sufficient condition, because here we assume the dimension n is not very high. By checking the cost at each stationary point, we can find the final solution. So here we are going to calculate this gradient vector. So what's the dimension of this gradient vector? So how many elements do we have as the partial derivative? That depends on how many variables we have. We have n variables, right, from original cost function, and plus k penalties for equality constraints, and m penalties for inequality constraints. So L will be n plus k plus m. So this will be the dimension of this gradient vector. Let's first calculate those elements with respect to x and lambda. So they are basically similar to the optimization with equality constraints. So partial L by partial x will be the partial f by partial s. This will be the original gradient element of the unconstrained problem. And the second type of element will be this part. We calculate the partial derivative with respect to each x. And this third item will be this part. So here we assume G and U can change with x. So that's why the partial derivative will have element there. And we hope they're all zero. So this one will give you n equations because we have n such elements. Okay. A second, partial L by partial lambda k. So this is exactly same as the equality constraints. So we have a k such equations. So equality constraints will come to here. So we take over all the equality constraints by forming this gradient vector. The last element will be partial L by partial mu. Okay. So that will be U, right? If you calculate partial L by partial U, mu, basically you just calculate this, right? The partial, because the early element will be zero, so they are not depending on mu at all. So only the last item has mu. So this one will have. So this one will get something like U itself. So that's what happened here. The next question will be, so we know this partial derivative will be U, but if we let this U be zero, we are looking for stationary points of this Lagrange function. But from original problem, we know U can be zero or negative. It doesn't have to be zero. So which means if you assume that as such element to be 0, you only solve part of the problem, not the other part. It only give you one type of solution. There's another type of solution, the U can be negative, which means we cannot stop here. We also add another case when U is negative. Then when U is negative, the gradient vector will not have a 0 element in the dimension about mu. But in this case, if U is negative, we don't need to include such U in the L function, because the purpose of L function is that to find stationary points. If U is not 0, so such point not stationary points, we need to cross off such element from L, and only make sure the remaining dimension will have a 0 element for the gradient vector. So in this case, we don't need this multiplier mu. The mu can be 0. Okay. Does everyone follow? It seems that not many people follow. Okay. To explain, everybody understand this yellow part, right? The yellow part is pretty clear. The yellow part is actually from original the optimization problem with only equality constraints. So we just combine the original cost function with the price you pay for violating the equality constraints. So that's our L. That's a yellow part. This part we need stationary points. We need all the elements of gradient vector to be 0. They have to be 0. That's our stationary points. Okay. And for the green part, there's some uncertainty, because for the green part, they come from the inequality constraints. For the inequality constraint, there are two scenarios, both fine. The first one is this constraint will become equality constraint. If that's equality constraint, we deal with that one same as equality constraint. That's what happened here in this first line. That's scenario number 1. For scenario number 2, we cross off this element, but we make sure what we find from by solving the yellow equations can make the number 2 equation to be correct, which means whatever you solve in the yellow part, you plug into the inequality constraints, the U has to be negative. Okay, I repeat again. So for the yellow part, there's no room to negotiate. They have to be 0. So they will create some equation for you to solve. For the green part, there are two scenarios. First one, if the green part is 0, they contribute some 0 gradient element to your whole vector. Okay, which means the final solution will stay at stationary point of the entire L. Another case, the green part may not be 0. It can be negative. It's also okay, because you stay inside of inequality constraints. Then you need to test the yellow part for the inequality constraint. If also satisfied, that's also a solution. Okay, so that sounds like a more complicated, right? You have to make sure your brain is very clear to check both conditions 1 and 2. There's one simple approach to make it easier. If you want to do coding, use a computer to program. You don't want the computer. Definitely, today's computer can be very smart. They can behave like AI. You just describe what you want. They will just check condition 1, condition 2. You can make a code, but actually we want to find the easy way. Okay, so maybe you will ask me a question. So I don't want to struggle with whether I need to check 1 or 2, or how can I make sure I don't miss anything. I gave you one formulation. You just go ahead and solve that set of formulation that guaranteed to be solutions of either 1 or 2. So such a approach is called the KKT condition. Okay. So if you didn't completely follow what I said to check condition 1, condition 2, you just go ahead to replace the green part by those 3 inequality, or equality. If you solve those three, they give you a solution exactly equal to the original two scenarios. You don't have to check between one or two. You just solve those. Let's double check. So if U is 0, this one is true. Yeah, to check those three new equalities or inequalities to be equivalent, we need to make sure the solution of the left will have to be solution of the right, and then the solution of the right has to be the left, right? So if U is 0, if U is 0, this one's hold, this one hold. This one is from the original assumption. Okay, if U is negative, if U is negative, yeah, this is true. And because mu is either positive or 0, and we need to make sure if it's negative, we need to get rid of that one from L. So this one has to be true. So mu has to be 0, such as you can get rid of that atom from the original L function. Okay, so you can also check the solution of the right has to be solution on the left. So they're completely equivalent. So such conditions are called KKD condition, Karush-Kuhn-Tucker conditions. So you can search for its name and for details. But anyway, this is a very useful condition, so you can easily code your solvers to find the solution of the optimization. To visualize what such condition mean. So the right circle indicates the gradient vectors or the values of the gradient or the cost function of original f. Okay. So let's assume the x star to be the final solution. And when we add this inequality constraints, we'll introduce this shadow area. So we want to find a solution only inside of that shadow area. The shadow area, including the boundaries, can be together define a feasible solution. So if the stationary point of original cost function stay inside of this shadow area, so what does this one mean? We only just need to make sure that point can satisfy the inequality part. So by plugging this stationary point into the inequality constraint, and we find out that U is negative, which means it stay inside of shadow area. So you don't only need to solve this yellow part, right? Don't worry about that inequality constraint. That's one scenario. That's case number 1. This is 1. For case number 2, the original stationary point stay outside of this shadow area, which means that cannot be a feasible solution. So we have to find some point which is close to that stationary point, which will be this new S star. The new S star has to be stay on the boundary of this inequality constraint, right? Because if it's not on the boundary, if somewhere inside, this point will be closer. That one will have the smallest cost. So if we reach the yellow part problem, if that station point inside of shadow area, don't worry about the green part. If that point is outside of shadow area, so boundary of the shadow area has to have a point which to be the new solution. That's what exactly this KKD conditions are talking about. Okay, yeah, this is just geometric interpretation, but if you don't want to develop any geometric method you just simply solve this set of equations or inequalities that can give you the solution. They find you all kinds of solutions, then you just check the function value. The smallest one will be the final solution of your problem. Any question? Okay, let's move on. All right, to summarize, how do we solve the optimization problem with both equality and inequality constraints? So we have a cost function, we have equality constraints, we have inequality constraints. First, we introduce the L functions, which is linear combination of original cost, penalty of due to the violation of equality constraints, and the penalty of from the inequality constraints. We will make sure the mu, the penalty, to be a non-negative. Then we introduce the KKT conditions. Okay, then we'll have a set of equations or inequalities to solve. Okay, then finally we just find the smallest F value from all the candidates. All right, let's use one example to explain what happened with this inequality constraint. So this is the original problem with the cost function and equality constraint. We have solved this problem. So we know the solution. There's two station points of the L, and this one will be the solution, right? That's what we know. But now we want to add inequality constraints. The inequality constraint says 2s plus y cannot be less than 12. 2s plus y equals 12 means a straight line. And if it's not less than 12, it means one side of the line, including the line itself. Okay. So if we convert this inequality to the standard form, which is u is equal to or less than 0, so will be 12 minus 2s minus y is less than 0, equal to 0. Okay, so if you draw that line, that's this straight line. The straight line will intersect with the circle at 2 points. And only on one side of the line will be the feasible solution, including the line itself. So which means original solution at this point is become not a solution anymore. So this point, because that's outside of the region. Okay. So then you may wonder, how about this point? Yeah, this point is still feasible solution. It stays inside of the shadow area. But unfortunately, this one has a lot of cost, right? This cost, if you remember, this is like a 225. There's definitely some other point which give you lower cost. Like for instance, this point will be cheaper, and this point could be even cheaper. But how can those points become the solution of the Python problem? Okay. Let's try to use our method. Okay, so that's feasible regions, and so if you solve the gradient vector, so there will be some candidate solutions. So first is from the original problem. Second will be this boundary point. So we're going to pick the solution from those three. So this one has higher cost. So the blue and the green one are more likely to be the solution. So if you check the cost, one will be the solution. So I draw the green arrows indicate the directions for the cost. F function can increase the value. So without constraints, those points cannot be solution, right? Because we have to move them in the opposite direction to reduce the cost. But because we have equality constraints, which is equivalent to add 2 arrows to each point. One is pointing to the center of the circle. The other is pointing outside of the circle. So at each point, if those arrows, they cancel out, that point will be a candidate solution. So now you see for the orange point, this is still has all the arrows canceling out at that point. So that's still a solution. But for the red one and the blue one, if we only just check the arrows in green and orange, they don't cancel out. The orange in the same direction, but the green indicate some other direction to move this point. Right? like there seems to be another force to move along the circle. But if we also introduce the force, each force due to the inequality constraints. So the physical meaning of this blue arrow is if you violate this inequality constraints, there will be additional force or penalty added here. This one. So if this point move inside of this region, this blue arrow will disappear. There's no penalty. But if you move outside of this shadow area, then there's a huge penalty. That indicates the increase of the penalty due to violation of this blue inequality constraints. So at the end, that make this blue point and the red point both be candidate solution, because even the orange arrow, they don't cancel out each other, but the green and the blue help the total arrows at each point to cancel out. So for this case, we have a 3 candidate solution. The next thing is just check either the blue one or the orange one or the red one, which one have the minimal cost. So that's a geometric interpretation of this the process to solve this problem. Let's go ahead to check our method using the Lagrange multipliers. So we have L with the first part from cost function, second part from equality constraints, the third part from inequality constraints. The next step, we first calculate the yellow equations, which include the partial L, partial S, partial L, partial Y, and the partial L, partial lambda. So this is equivalent to solve solving the optimization with equality constraint only. But definitely here we also introduce lambda. Then for the partial L, partial lambda, we have to compare two cases. The first one is if this is stay inside of this shadow area, so the U will be negative. The second will be U will be 0. Okay, so U is 0, so that's equivalent to the equality constraints. So by the KKT condition, so that can be translated into those 3 equations or inequalities. So we just need to solve those 3 equations together with those. And together, there are only 3 solutions. You can design some method, maybe by Gauss method, to help you to find a solution. Okay, so finally we have a 3 candidate solution. So orange one, this one is the stationary point of original cost function inside of the shadow area, but that cost is too much. This is not the final solution. And for the red one and the blue one, the red one will have the minimal cost. So finally, this red one will be the final solution of the problem. They stay on the boundary of the inequality constraints. Okay. So we still have this conclusion at each candidate solution, all arrow will cancel out. But you don't have to use this geometric method. You only just need to follow the procedure we talked about in the class to solve the problem. Okay. So I will see you on November 10th. Kaiyang, GTA is in the back of the room, and he will give you the lectures about the toolbox, MATLAB toolbox. Please come to the class next week.